dari negara untuk Eropa misalkan. Nah,
Betul.
nanti kalau itu saya share misalkan ya ininya skemanya mungkin kalau Pak Stevin bisa sesuai ininya topiknya mungkin bisa bantu untuk
Baik,
jadi
Prof ya.
bagian dari itu ya. Berarti.
Iya, yang sekarang ini sayang sih saya udah keburu apa namanya diskusi dengan partner di Unpad, Prof, untuk yang
Hmm,
PF itu loh, International Science Partnership Fund.
gitu ya.
Expression of interest-nya baru tutup sih 2 minggu lalu ya, gitu.
Hmm,
Terusnya
ya
ini
ya.
lumayan banyak sih peluang, mungkin tiap 6 bulan bakalan keluar terus. Jadi nanti
Hmm,
kita kita itu aja, Prof, diskusi gitu ya. Yang so,
iya,
so far sih jadi co-investigatornya proyeknya teman-teman di fisika.
iya.
Cuma
Kalau
kayaknya itu mm,
hmm, kalau saya kan sebetulnya eh, interestnya itu lebih ke ini ya ke material.
baik,
Biomaterial sebetulnya kita risetnya untuk fotokatalis ya.
baik.
Fotokatalis untuk photoelectrochemical water splitting, untuk synthetic dyes photo degradation. Nah,
Iya, ya.
terus yang metaliknya kita buat juga elektrokatalis. Ya, ada yang
Baik.
untuk electrochemical water splitting, terus juga untuk seperti direct ethanol fuel cell ya, elektrooksidasi etanol.
Iya, iya, ya.
Terus kita juga ada mulai kolaborasi sama Pak Lewat di UI ya, sama Pak Fato Abdi ya, kenal ya. Yang
Oh,
sekarang pindah
fatwa
ke ya, sekarang pindah
City
kan
University
ke itu ke Hong Kong ya.
CTU.
Heeh. Nah, kita makanya sekarang buat bimetalik katalis untuk ini eh, oksidasi gliserol
Right,
seperti
ya.
itu. Kalau kalau Pak Steven juga kan sebetulnya semikonduktor juga kan ya?
Iya, lebih saya ke katalis di high temperature fuel cell di solid oxide, juga
Hmm.
untuk alkaline fuel cell sama alkaline electrolysis.
Oh ya berarti sebetulnya ini ya
Ada
ada keterkaitan ya?
Misalnya banyak sekali, Pak. Iya, jadi saya main banyak di oxide ya.
Ya 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 oke. Berarti kalau electrochemical impedance spektroskopi ini juga ya?
Iya,
Pembahasannya
ada.
bagus ya?
Iya,
Oh, kita kan sebetulnya ada rencana ingin buat workshop tuh di Jakarta. Kalau pesertanya mahasiswa S1. Mas
iya,
Davin
iya.
akan ada waktu nggak ya kalau ngasih workshop pas nanti ke sini?
Waduh, kayaknya
Padat ya? Padat ya?
iya, harus dipasin ya. Iya,
Hmm. Iya ya. Nanti gini aja kalau kira-kira ada waktu, kalau memungkinkan jangan memaksakan. Kabari saya nanti biar saya yang menyesuaikan jadwalnya di sini. Kami yang
baik,
menyesuaikan jadwal.
Prof.
Kayak
Ya,
gitu. Ini
ya.
mungkin nanti ini lebih ke ini aja apa nama introduction to EIS gitu.
Oke.
Seperti itu. Dasar lah, dasar. Kemudian sedikit mungkin ke interpretasi datanya gitu ya.
Ya, ya, ya. Ya,
Oke.
ya nanti coba diatur, Prof. Ya,
Ya boleh boleh.
ya.
Eh, berarti rencana Agustus ya?
Rencananya sih Agustus ya, tapi cuma 1 minggu aja.
1 minggu ya? Ya tapi kalau tidak memungkinkan tidak apa-apa. Nanti saya coba kontak teman-teman yang lain.
Baik,
Eh,
baik.
eh,
Ya,
baik, udah lewat ya Pak Stevin. Kita mungkin udah bisa mulai ya.
ya.
Oke, silakan Bu Citra kalau mau ini, kalau mau dibuka dulu. Mic-nya belum, belum on mikrofonnya. Bu Citra, suaranya nggak jelas. Ayo coba tes mic. Tes ya telepon deh. Baik, Pak Stevin, silakan dimulai saja. Ini yang mau buka acaranya ada kendala dengan mic kuliahnya. Teman-teman mahasiswa ya, saya perkenalkan ini Dr. Stevin Pramana dari Newcastle University, dari Faculty of Engineering ya, Dr. Stevin ya. Beliau akan
Betul.
menyampaikan tentang semiconductor material ya. Ini eh, sedikitnya kita sudah singgung di kuliah ya. Dan beliau akan menyampaikan tentang dasar dan aplikasi dari semiconductor material itu. Dr. Stevin, saya persilahkan untuk menyampaikan kuliahnya. Terima kasih untuk kesediaannya nih jauh-jauh dari UK ya. Jam 10
Baik.
lewat 9 dari di sana ya. Oke, silakan. Nanti
Ya.
setelah beliau menyampaikan kuliahnya, eh, nanti akan ada kesempatan untuk mahasiswa untuk berdiskusi dengan beliau. Silakan Dr. Stevin.
Thank you very much, Prof. Setiabudi. Selamat sore, teman-teman semua, adik-adik. Thank you for Prof. Setiabudi for inviting me to give this guest lecture. Prof, is it okay if I speak in English or
It's okay. You
Bahasa?
can deliver your talk either in English or in Bahasa. I think that's fine.
Okay, brilliant. Okay, right. So good afternoon again, students at UNJ. So today I'm going to deliver a guest lecture on semiconducting materials. But then we are going to focus mainly on the fundamental aspects and a little bit of the applications from the photocatalysis kind of point of view. So again, before we start, when we actually want to discuss about these materials that behave in the semiconducting, we can't really deny, or we can't really avoid that we have to learn a little bit about band structure of solids. I'm not too sure whether you have learned about this, but I'm going to cover from this. Then following up with the concept of bands, yeah, valence, conduction, and band gap in metals, insulators, and semiconductors, as well as the concept of intrinsic and extrinsic semiconductor. Then a little bit about direct and indirect band gap semiconductors. Then wrapped up with the applications in the photocatalysis. So last year I had a privilege to visit UNJ. So mainly I was welcomed by colleagues from the physics department. So it's just missing Prof. Setiabudi at that time. So we had quite a fruitful discussion. So I delivered kind of a little bit of talk on what my research is all about here at Newcastle, and managed to actually capture a kind of a few photos with the ONG background. Just to give you a little bit of my background and expertise. So I'm still Indonesian, saya WNI, and I graduated from for my S1 from NTU, Nanyang Technological University in Singapore, and then I moved and continue all the way to PhD still at the same university, NTU Singapore. Then I had the chance to continue my postdoc at Imperial College London in London, UK. Then in 2017, I moved to Newcastle to become a faculty member here in the Department of Engineering. So I graduated as a material scientist from NTU. Then for my first postdoc, still in the same department of materials. But then when I moved to Newcastle, I'm still doing materials science related kind of research, but I'm kind of housed in the department of or School of Engineering at Newcastle. But my main interest is still mainly on the kind of the chemistry and physics of materials, especially the how we can actually manipulate defects so that we can tailor the properties to both from the optical, from the electronic, and also from ionic or the magnetic properties. So I'm just going to start with the concept of this band structure. So probably some of you might have learned here in the kind of A-level equivalent kind of chemistry. So I'm just going to kind of have this as kind of a two-way discussion. So if let's say some of you can just open your video, open your mic, then it would be much appreciated. So we know that the electrons of atoms, if they are actually isolated, meaning that you have separated atoms, so they actually occupy fixed and discrete energy levels. Then with this Pauli exclusion principle, so does anyone still remember what Pauli exclusion principle is? So basically, the principle says that within one energy level or one orbital, so each orbital can only be occupied by uh, 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 the two electrons. Okay, so when these two atoms actually approach each other to form a bond, so the Pauli exclusion principle would be violated if the energy levels are not different or did not change. So, and because of that, then the energy level must actually split to form new energy level. So if let's say I move to the next slide here. So that's where we have a diagram with the y-axis of electron energy, and the x-axis kind of just a separation between atoms. So if let's say we have one atom, so you know that the electron kind of orbital splits between core level and valence kind of level. So the valence electrons here occupying the kind of the energy far away from the nucleus or the core innermost electrons. And these valence electrons actually involved in bonding. So now, if let's say we have two atoms, interacting one another, so meaning that they actually brought close enough to interact. So what we mean by interacting here is actually the electron interacting, they will form bonds. So the bonds can be in the form of whatever metallic, covalent, or the ionic bonds, depending on whether you kind of share of electrons or donating or receiving the electrons. And because of that Pauli exclusion principle, so this valence electron of these two atoms, when they bond to each other or when they interact, so they cannot be in the same kind of energy level. So they have to actually split to satisfy those the Pauli exclusion principles. So one basically shift to higher energy, and the other basically shift to the lower energy level. And probably when you understand this from the kind of chemical bonding point of view, so one will actually involve in the kind of bonding orbital, and the other one will involve in the kind of the anti-bonding orbitals. And obviously, the electrons will only occupy the new orbitals with the kind of by filling the lowest energy level first. So that's kind of if we looked at from kind of an idea of two atoms. So now when we actually have a couple of kind of sets of atoms coming together, so this splitting of these electrons will become more pronounced. Yeah, so if let's say you have two, then from one electron orbital, it has to be split into two different energy levels. But then when you actually have 3, 4, 5, then you'll end up with kind of splitting more. So now you can imagine when we actually kind of have bulk number of atoms rather than just small number of atoms, then we can just simplify this because the separation in each kind of orbital here is actually very small. That actually forms bands. Yeah. So that's just a concept of a band structure of solids. So in the core level of electrons, so it's not going to be affected because kind of there's not involvement in bonding. But then what we are interested in terms of modifying or tailoring the different properties are the electrons that are located in the outermost kind of shell here. And from that, then we can understand a valence band here, then separated by a band gap if there is any. Then after that, on the kind of the higher state here, we have the conduction band. So again, depending on this the type of material. So we have, for example, just classify this based on 3 types. We have metal, semiconductor, and an insulator. So there may or may not be kind of sizable or kind of separated enough energy gap between this energy level that shift from the kind of lower energy state to the kind of the higher energy state. If we can identify this band, this gap between the first kind of lower band and the higher band, that's just simply a concept of band gap, with normally the notation of the band gap energy here as Eg. So typically, the way that we kind of put a nomenclature of the semiconductor and an insulator is just roughly around 4 electron volts. So hopefully you still remember a concept of electron volts. So later I'm going to elaborate how we can convert electron volt into joule or joule per mole, or just simply into wavelength or wave number. So in the metals, so basically the valence band is kind of overlapping with this conducting band, or partially filled or empty overlapping conduction band. And because of that, then we can't really observe the band gap, and the electron can easily go towards or excite towards the conduction band, and they can actually move freely. This concept of metals, we've got the kind of a sea of electron clouds, and because of that, the electrical conductivity is very high. But then in the insulator, the band gap is actually very far, so or large. So the band gap is typically higher than 4 electron volts between the filled and the filled valence band and the empty conducting. Whereas the semiconductor, so around about kind of in the range of less than electron. So what is a kind of a definition of a valence band? So this is just simply the range of the energy levels that are occupied or that are fully occupied by electrons at equilibrium, or sometimes in the kind of the organic, you have like HOMO or LUMO. And in semiconductor here, an insulator, that's just simply kind of lies below the band gap. And this contains the electron kind of tightly bound to atoms, and they kind of they're involved in bonding when kind of the atoms kind of interact or kind of come close to one another. Then how about the conduction band? So the conduction band here is just the band where the electrons from this valence band can actually be excited. So typically at equilibrium, they are kind of normally vacant. So when the electron kind of gains sufficiently high enough energy, so the energy can come from, for example, you shine with light, with photons, with a certain amount of energy. Then you can actually excite the electrons, or simply by kind of thermal excitation, that's also be possible. And when electron actually moves or jump into the conduction band, then they become kind of mobile charge carriers, and they're actually involved in the electrical conductivity. And again, this band structure is basically an understanding of this band structure at temperature of 0 Kelvin. So the elemental semiconductor, as you know, if you just kind of map the periodic table, so just in the group 4b, so including germanium and silicon. And not only kind of elemental semiconductors, they're very useful in most of the kind of electronic applications. There are lots of semiconducting materials that are actually formed as a compound. So for example, compound semiconductors, we can actually have in group 3 and 5. So for example, gallium nitride, gallium arsenide, indium phosphide. Also, if we combine group 2b with group 6b, then we can find cadmium sulfide, cadmium selenide, and cadmium telluride. So typically the kind of the group 2 and 6b are very good materials for example, in photocatalysis, whereas the 3 and 5 here, gallium nitride, gallium arsenide is also useful for kind of in the semiconductor for kind of photonic materials. So now we get kind of just a concept of these semiconductors from the band structure. So we can actually understand the concept of electrons and holes, or how we can actually control the properties, whether just by thermal excitation, by knowing the concentration of holes and concentration of electrons in the material, or we can actually purposely control the properties by simply using doping. So the dopant here must be kind of coming with different number of electrons. Yeah, so you have, for example, group 4 silicon. If you try to dope with, make it, for example, NOP type semiconductor, then you have to dope with either group 5 or group 3 kind of element in the periodic table, and that's simply what we call as extrinsic semiconductor. So why we are interested in the extrinsic semiconductor? Because typically within kind of a certain temperature range, the conductivity is controlled by the amount of dopant. So, and not so much kind of controlled by the temperature. So I'm going to kind of explain this in the map, in the graph, the relationship between intrinsic and extrinsic as a function of temperature. So again, as we discussed just now, the energy band gap between the valence and conduction band is pretty small, typically less than 4 electron volt in semiconductors. And as temperature increases, or as we kind of give energy in the form of, for example, photons, there some electrons will possess enough energy, so in this case thermal energy, to be promoted from the kind of fully filled valence band to the vacant conduction band. So obviously, when the electrons actually leaves the valence band, it will actually leave a concept of hole here. So in the valence band, because the electron moves to the conduction band. Yeah. So when the electron actually moves, is it okay? When the electron moves hole, then another hole is created. So in a way, when the electron is actually moving towards one terminal, then we can actually understand the concept of hole moving in the opposite direction. So the holes appears to act as kind of positively charged electrons, and they carry an electrical charge here. You know that the electron carries kind of negative electrical charge. So when a voltage is applied to the material, so the electrons in the conduction band will accelerate towards the counter kind of charge, is just the positive terminal, whereas the holes in the valence band will move towards the negative terminal. So let's look at the semiconducting material of a material with both valence electrons, so for example, silicon or germanium here. So the circle here is just showing an electron. So we've got 4 valence electrons. So when the electron is actually excited to the conduction band, so it will actually leave behind a hole in the valence band. So when the electron moves here, just basically hopping electrons from one side to the other in the to the vacant here in the name of hole here. So basically, we can understand that the hole is actually moving to the opposite direction there. So kind of in the energy diagram here, so when the electron moves to the positive side, when we apply the potential difference here, then the hole, which carries positive charge, will actually move in the opposite direction. So the current is controlled, or this is conducted by this movement of both electrons and holes in semiconductors. So to basically calculate the conductivity, or you can actually convert this into resistivity, just 1 over sigma here. So the conductivity here is related to the amount of concentration of charge carrier multiplied by just simply the mobility. Yeah, because we have both electrons and holes, then we have to actually take into consideration of those. Both the mobility of electrons is typically higher than mobility of holes. So, and hence the conductivity here, sigma, is given as N, the concentration of electrons in the excited conduction band, multiplied by this Q. Q is just the elementary charge, or the charge on electron is just a constant, given as 1.6 times 10 to the power of minus 19 Coulomb, multiplied by this mobility of electrons given here as mu subscript N. So NQ mu N, plus then we just have to take into consideration the factor of from holes. We just simply the same thing. Rather than N, we got the P, just a concentration of holes in the valence bands after the electrons leaving the valence band to the conduction bands, multiplied by the elementary charge, multiply now the mobility of holes, P. Yeah, so sigma is just simply NQ mu N plus PQ mu P. So in the intrinsic semiconductor, so we understand now for every electron that is actually promoted from the valence band to the conduction band, it will actually leave behind a hole. So one electron will leave behind one hole in the valence band. So and hence, we can actually just put this equation of just the number or the total concentration of the electrons in an intrinsic semiconductor, and I will just simply equal to the Pi in the intrinsic semiconductor. Because one electron will leave behind a hole when they get excited from one band to the other. So the conductivity of an intrinsic semiconductor now, we can just lump together because we have the total number of holes and electrons equal. So rather than NQ mu N plus PQ mu P, then we can just simply lump this together because the N and P equal to Ni. You just simply sigma equal Q times Ni. Now the intrinsic concentration of electrons, which is the same as intrinsic concentration of holes, multiplied by sum of the mu N plus mu P. So we know that at kind of absolute zero temperature, so the electrons are basically populated only in the valence band, and the conduction bands are is mainly vacant or unoccupied. So as temperature increases, as we discussed just now, there's a greater probability that the energy level in conduction band is occupied. So the probability here is equal, and hence it is translated into the total number of identical concentration of an electron. So now when we take into consideration the temperature here, so N is just equal, just now Ni equal Pi, so that's the intrinsic semiconductor. You can actually lump together here with a factor of the effective mass of electrons and hole. As such, you got the N naught exponential of minus. This one is just similar to what you understand in most of the chemical reaction, like Arrhenius equation. It's just exponential minus of the energy. So in this case is the band gap energy, and the band gap here, Eg, divided by 2 times Boltzmann constant times temperature in Kelvin. Yeah, so the constant of the N naught here is just simply 2 times 2 pi kBt divided by the Planck's constant square to the power of 3/2 multiplied by this component coming from the effective mass of electrons and holes to the power of 3/4. So now when we just put the Ni here, so from this equation here, taking into consideration this N naught, so you just the conductivity here, sigma is just simply N naught multiplied by Q multiplied by mu N plus mu P exponential minus Eg over 2 kBt. So that's kind of the a few formulae that are useful when we want to understand the concentration of holes, electrons, and the concept of the relationship between this the amount of hole and electrons to the band gap and temperature. So I've prepared kind of 1 or 2 examples how we can actually make use of that formula. So for example, if we have germanium, semiconducting material in group 4 in the periodic table, we are given a lattice parameter of such, so 5.6575 times 10 to the power of minus 8 centimeter. So hopefully you know by now from the other module about crystal structure or crystallography. So this lattice parameter is just the kind of the unit cell dimension. So unit cell is just simply a smallest repeating unit, because by definition, crystal is kind of an ordered arrangement of atom in 3-dimensional. So what we need to know is just the smallest repetitive unit, just a concept of unit cell, in which if the unit cell is actually translated in 3 dimension, you will actually capture the whole solid volume. So this lattice parameter here is in the range of that, typically in the range of a fraction of nanometer or in kind of a couple of angstrom. At 25 degrees Celsius, we are given the electrical resistivity rho. So just on conductivity sigma, rho here is 43 ohm centimeter. So just now the unit for conductivity is just simply 1/ohm multiplied by 1 1/ohm multiplied by 1 kind of length, 1/centimeter or 1/meter, and 1/ohm is just simply another unit of Siemens. So rho 43 ohm centimeter, and we are given a band gap of 0.67 electron volts, and we are given the mobility of the carriers of electrons and hole as such, 3,900 and 1,900 centimeters square over volt over second. Then you have to calculate the number of charge carriers, the fraction of total electrons in the valence band that are excited into the conduction band, and lastly the constant of NO just now. The N or Ni is equal NO exponential minus EF divided by Eg divided by 2 kB times T. And we are given the electron, the elementary charge of the electron, the charge on an electron is just simply 1.6 times 10 to the power of minus 19 coulomb. And we are given the Kb, or Boltzmann constant, of 1.38 times 10 to the power of minus 23 joule per Kelvin. So we know that Ni, the concentration of electrons is the same as concentration of holes here. It's just simply the sigma here divided by Q multiplied by mu N plus mu P. And from the resistivity, conductivity is just simply 1/. Just to kind of another note here, please make sure that you understand the difference between resistivity and resistance, conductivity and conductance. So please don't get confused. So basically, the resistivity and the conductivity, that's a material properties. When you actually take into consideration the geometric, basically the length and the kind of the cross-sectional area, then you will end up with the resistance or conductance. So the conductivity just simply 1 divided by resistivity, and just 1/43, which is just simply 0.0233 Siemens per centimeter. So now we have Ni just simply that, 0.0233 divided by the elementary charge, 1.6 times 10 to the minus 19 multiplied by the sum of those mobilities of electrons and holes. And what we have there is per centimeter cube, we have 2.51 times 10 to the power of 13 number of electrons. Then how about the total number of holes? It's just going to be identical, because what we are concerned here is the intrinsic semiconductor. So now to solve the sub question B, if you want to know or understand what is actually the percentage or the fraction of the total electrons in the valence band that are excited into the conduction band, then we have to calculate the total number of electrons within unit cells, and later on you can actually calculate the total electrons per unit volume of centimeter cube, because just now we calculate the total number of the electrons here, and I here is per centimeter cube, because of the unit used here in the resistivity and conductivity per centimeter, and we've got the mobility in per centimeter square. Yeah. So I'm just going to elaborate a little bit on the crystal structure here. So we've got the lattice parameter of such. So if you don't really know the structure of germanium or structure of silicon, so here how it looks like. So basically it is like if you consider here is kind of the unit cell, and the symmetry here is cubic. So you have the atoms occupying the corner of this unit cell. So you got this, yeah. And for in the concept of crystals, so the atoms is actually occupying a corner. So within this unit cell, it is only sharing 1/8, because the concept of unit cell must be repetitive. So this corner atom here is actually shared by another 8 kind of surrounding kind of unit cells. And basically you've got this just only 1/8 that if you just account only for this particular unit cell. So you got 8 there, so you just simply 1/8 times 8, so you got 1 corner atom. Then followed by you have the atoms in the face. So if you have ever heard a face-centered cubic, so that's how it kind of position. So on top of the corner atom, so we also have over the face of the cubic at the center here, we've got another one. So for the face kind of atoms is only shared by 2 unit cells, because you've got the right one and another one is left. So for example, here you got the top one and the bottom one. So you got 1, 2, 3, 4, 5, and 6. So and hence you've got 6 face divided by 2. You've got 3 face atoms, and you have basically internal or kind of the inside atoms here. When you understand the concept of defects, so typically this could be a position where kind of tetrahedral interstition is normally happening. So we have 4 inside atoms here, kind of wholly kind of owned, wholly kind of owned by this unit cell. So in total, there are basically 8 atoms in this unit cells, coming from 1 corner, 3 face, and 4 inside atoms. So how about the volume of a unit cell? Because we know that the germanium crystallizes in a cubic system. So the volume is just simply A by A by A. So we got 5.6575 times 10 to the power minus 8 to the power 3. And that's what we've got. So 1.81 times 10 to the power minus 22 centimeter cube. Then how about the total number of electrons per centimeter cube? So we know that in one unit cell, there are 8 atoms. And in one atom, so there are 4 valence electrons. Yeah, we got 8 times 4 here. And we just kind of divided here by the volume of the unit cell here. So what will end up here is just simply 1.77 times 10 to the power 23 electrons per centimeter cube. So in 1 centimeter cube, so you're expecting to have 10 to the power 23 electrons. And the amount of the electrons that are excited at that particular temperature that kind of leads to that particular resistivity or conductivity is just simply the total number of Ni just now calculated in the previous slide, 2.51 times 10 to the power 13 divided by 1.77 times 10 to the power 23. So what we have there is just simply 1.42 times 10 to the power minus 10. So only 1 times 10 to the power minus 10 kind of fraction that is actually jumping to create this electron kind of hole pair. Yeah. So then the next one here is we are asked to calculate the n naught, and we are given a band gap of 0.67 electron volt. I'm pretty sure you know already how to convert the electron volt into various unit of energy, but just for kind of the sake of discussion here, an electron volt, the concept of electron volt is just an energy given to accelerate an electron. So the electron here carries a charge of 1.6 times 10 to the power minus 19 through 1 volt of electric potential difference. So you have one electron multiplied by 1 volt, then basically this will give out the energy. So you've got Coulomb multiplied by volt, that will give you Joule. So the work done on a charge is just simply charge multiplied by voltage. We know that the elementary charge or the charge on an electron constant just simply 1.6 times 10 to the power minus 19 Coulomb. So the kind of the energy this given to that electron here is just simply charge multiplied by 1 volt. It's just giving us 1.6 times 10 to the power minus 19 joule. So this is a kind of easier description or understanding of an electron volt. So 1 electron volt is just simply 1.6 times 10 to the power minus 19 joule. Yeah, so electron volt is the energy. If you want to convert electron volt into joule per mole, that's what we understand in the, for example, the bonding energy or the activation energy in most of the chemical reaction. Then what we need to do is just to multiply this with the Avogadro's number, which is just 6.023 times 10 to the power of 23. So what you end up is just simply 96485, yeah, kilojoule joule per mole. So that's the concept of electron volt, and hence the band gap here, 0.67 eV, just simply this multiplied by that, so just simply 1.07 times 10 to the power minus 19 joule. So why do we need to convert the EG into joule? It's just simply we are given the Boltzmann constant as joule per Kelvin. So you can actually convert the Boltzmann constant instead of the band gap here into EV per Kelvin, just basically using the same concept there. So the EG of 0.67 EV, now in joule, you got the Boltzmann constant KB, and N naught here is just simply N divided by exponential minus EG divided by 2 kBt. So the N naught here is just plug those numbers. 2.51 times 10 to the power of 13 exponential. So now the EG in the joule minus divided by 2 times the Boltzmann constant multiplied by temperature in Kelvin. So what you have there, the N naught there is just simply 1.14 times 10 to the power of 19 carrier centimeter. Then just giving you a bit of explanation or example how we can actually make use of those formula. So when we actually put this electrical conductivity in the intrinsic semiconductor with the unit of Siemens per centimeter or 1/ohm per centimeter as a function of temperature. So as temperature increases, because the total charge carrier basically increases kind of exponentially, in this case, for example, in germanium, so the electrical conductivity will actually increase. Yeah, as T increases, charge carrier increases, more charge carrier for conduction increases, and hence this actually increases. In metal, so for example, aluminium here, when the temperature actually increases, the electrical conductivity actually reduces. It's just simply because as temperature increases, so the atom that is actually bound to the lattice actually vibrates, and that actually reduce the mobility of these electrons. Then what happened in semiconductors? Yes, of course, this electron as temperature increases will actually kind of get disturbed or gets more scattered. But then the impact of that is actually kind of low compared to the increasing in charge carrier. So the mobility decreases is actually much weaker dependence than the kind of exponential increase in the number of charge carrier. Remember the scale here, even though this charge carrier is kind of increasing, but still it is actually much lower in of the value of conductivity. The orders magnitudes different. Yeah. So that's how we can understand the conductivity or resistivity as a function of temperature in semiconductor and in. So now we move on to extrinsic semiconductor, because practically it is not easy or straightforward to control the properties, especially the electrical conductivity of an intrinsic semiconductor using temperature, because when there is a slight variation in temperature, this will actually change the conductivity significantly. So we need to find a way that can control the properties difference or the properties modification, not coming from temperature, but coming from more kind of tailored way or more simpler way, by just simply adding the the impurities or dopants in the extrinsic semiconductor. So adding these impurities, dopants with different number of valence electrons, will create this extrinsic semiconductor, and the conductivity just simply depends on the total number of these dopants, because that impurities will basically donate the electrons or donate kind of the creating the holes, and this the type of dope. And obviously within this certain temperature range, because it is controlled by the total number of dopants, the conductivity is not kind of the conductivity does not vary significantly with temperature. It's kind of pretty much quite plateau, as temperature varies, of course, within a certain temperature window. Kind of just a recap there. We know that at absolute zero temperature, the electrons are all in the valence band, and the conduction band are unoccupied. As temperature increases, so the number of electrons in the conduction band increases, and hence the conductivity will vary. So let's have a look on the first type here, which is the N-type semiconductor. So in the N-type semiconductor, for example, if we add an atom with 5 valence electrons, so with the silicon germanium we have 4 valence electrons, but then for antimony, for example, we have 5 valence electrons. And if you looked at how the bonding is happening in the silicon in the presence of the impurities of Sb, antimony. So there will be an extra kind of electrons, because of the definition of the the bonding between silicon and between the silicon and antimony. So we only need 4 and 4 coming from the antimony, and hence we have a free conduction electron from this Sb. So if we actually put this in the energy diagram here, so the extra electron here is not kind of tightly bound to the atoms, because only 4 that are involved in the bonding with the silicon. So only a small increase in energy. So now the electron is actually enters an energy level slightly just below the conduction band. Yeah. So the rest of here is coming here, and only small increase in energy rather than Eg here for the electron to be excited from the valence conduction band. So what we need here is just an Ed for the electrons to actually get involved in the conduction. So the energy level just below the conduction band there is just simply called kind of energy level of this donor state. So rather than Eg here, we have a new nomenclature here as Ed. So hence this an N-type dopant donates a free electron for each impurity. So one antimony will actually donate 1 electron. So now the energy gap that will control the conductivity is no longer Eg, but rather Ed here. Okay. But again, now what we need to understand here is completely different from intrinsic semiconductor, because what we need for the electron to jump here is just Ed here. So when the electron is actually jumping here, this yellow electron here, there will not be any corresponding hole created when these donor electrons enter the conduction band, except if you try to excite the valence band electrons, and obviously the hole will actually be created. So here is still the case, the electron hole pairs were created when the thermal energy causes electrons promotion or excitation from the valence to conduction band. However, the total number of this electron hole here is only significant at high temperatures. And that's why we can easily control the amount of these donor electrons by just simply controlling the total number of the donor atoms. So one donor atom in 5 plus in 5 valence electron will actually donate 1 electron. So in the kind of inverse understanding here, conversely here in the p-type semiconductor, rather than we add an impurity of 5 valence electrons atoms, so we actually add an impurity of gallium or boron now with 3 valence electron to silicon or germanium. And basically we don't really have enough electrons to complete the bonding with the silicons. So we need 4 electrons. And because of that, then a hole is created in the valence band here that can be filled by the electrons from other location in the band. So the holes here will act as the acceptors of the electrons. And now with this p-type semiconductor, so it only needs this energy kind of band gap rather than Eg. Now we have Ea here for the holes to be created and mobile in the valence. So these hole sites will create rather than a donor level. So donor level is the state which is closer to the kind of lower energy state of the conduction band, but this hole site just create an acceptor level closer to the kind of top energy level of the valence. So once the hole is created, when the electron is actually jump into this EA here, then the p-type semiconductor is then this hole will carry then carries charge. So please remember, every time we create kind of defect in chemistry, so the neutrality of the charge needs to be maintained, because now we are involving electrons, we are involving donor atoms, we are involving acceptor atoms, and hence kind of just a simple charge neutrality is just the concentration of holes per unit volume plus the kind of donor atom must be equal the concentration of electrons per unit volume plus the total number of acceptor atoms. By doing electron neutrality. So now if the extrinsic semiconductor is heavily n-type dope, which is kind of in most of the case, so basically just simply Nd, which is much bigger than the intrinsic kind of electron here, then the concentration of electrons here, we can just take into account the total number of dopant, in this case the donor atom. And similarly for holes, if it is heavily p-type dope, and the concentration of hole is just simply the same as the concentration of the acceptor atoms. So that's the a concept of this charge neutrality. So again, just to give you a little bit of illustration on how we can actually make use of that formula and understanding. So if you're asked to design a p-type silicon base, so it's a acceptor there. So now we are given a lattice parameter or unit cell dimension of such 5.4307 times 10 to the power of minus 8 centimeter. And we are given also a conductivity of such 100 Siemens per centimeter over a range of temperature. So you're asked to calculate the required concentration of acceptor atoms in silicon with the concentration of silicon atoms. We are given the mobility of the holes in silicon. Here is 480 centimeters square over volt over second. So we know p-type, so silicon needs to be doped with atoms with a valence of +3. So for example, gallium or boron. So we can just assume that the total number of intrinsic carrier is small, is negligible compared to the dopant concentration. So the conductivity here is just simply Na. So because we kind of we don't really take into consideration the Ni, so just Na times Q times mu P, and hence the total number of the acceptor atom, in this case, for example, boron or gallium, is just simply 100 Siemens per centimeter divided by the elementary charge multiplied by this mobility of holes, is 480 centimeters square per volt second. And we can calculate here what we need to achieve the constant conductivity of such with defined mobility of holes to be 1.30 times 10 to the power of 18 total number of acceptor atoms per centimeter cube. And kind of a similar idea of from the previous example. So what we want to actually calculate the total number of holes or total number of acceptor atoms per unit cell or per centimeter cube later on. So the volume of the unit cell is just going to be, because the crystal structure of silicon is the same as germanium, so it's forming like just now we've got the silicon atom occupying the corner, the face, as well as the 4 intrinsic side. Volume is just a cube, it's just going to give us 1.6 times 10 to the power minus 22 centimeter cube. And in a unit cell similar to germanium, there are 8 silicon atoms. And because we dope with assumption of +3 valence dopant, and there will be a contribution of 1 hole per dopant atom, and hence the total number of acceptor atoms per unit cell is just simply 1.3 times 10 to the power of 18 multiplied by 1.6 times 10 to the power of minus 22. So this 1.3 is just given here. We got the total number as such, per centimeter cube. So we have the total number of acceptor atoms here is that 2.0855 times 10 to the power of minus. So in the unit cell here, the concentration of acceptor atoms divided by the concentration of silicon atoms is just simply that divided by 8. So per silicon atom, we have to introduce 2.6 times 10 to the power of minus 5 dopant atom. So again, the issue here with the extrinsic semiconductor in the lab or in the fab company, fabrication company, we need to actually have not only high purity chemical, because we need to know the total number of atom per whatever moles of things that you put into the silicon, but also another possibility is you don't really want to have impurity coming from the manufacturing processes, and hence you need to actually have a clean room condition. Just simply we just looked at here 2.6 times 10 to the power minus 5 per silicon, or just simply you've got 26 dopant per million of silicon atom. So the requirement is quite stringent to make this processing possible. So now when we try to actually combine, or when you try to understand the effect of temperature towards the total number of charge carrier, in this case, we just take into account just the total number of electrons here, again, depending on N type or P type. So put this here as 1 over T, or 1000 over T of Kelvin. So at low temperature, the total number of charge carrier concentration is very low. And once it kind of has enough energy, kind of given this ionization, then it starts to actually you start to see the increase in the total number of charge carrier concentration. Then, if let's say we actually doped the material, here's some conducting materials, for example, silicon with extrinsic. So the total number of these electrons here is just going to be practically identical, because it depends on what's just basically plateau here, because there is very little contribution from the effect of temperature. because the extrinsic kind of semiconductor is heavily determined by the total number of impurity dopants, be it acceptor or donor. Then once it goes into a high temperature, then the thermal energy is sufficiently high enough to actually drive more electrons from the valence band to the conduction band. And the relationship with respect to temperature, if you still remember that this just it is increasing as a function of Eg divided by 2 kb. That's why we put this as n on the y-axis, and the x-axis here is just 1/t, because if you look at just now, the n equal n naught exponential minus Eg divided by 2 kb times t. So typically when we are trying to understand conductivity in catalysis, for example, or in semiconductor here, the x-axis is used in 1/t. This kind of the concept of this Arrhenius equation, and that's basically the slope. You can calculate the band gap coming from here. So kind of this is just the text. So when the temperature is too low, so the donor or acceptor atoms are not ionized, and hence the conductivity is small. As temperature increases, the ionization process completes, and electrons, a hole contributed by this donor, becomes available for conduction, independent of temperature here, given as extrinsic. As the temperature even higher, the thermally generated carriers begin to dominate, and the behavior approaches to that of intrinsic kind of semiconductor, and the effect of dopant is lost. And at very high temperature, the conductivity decreases again as carrier dominates. It's not shown. Just now we have a condition here. If let's say we have the total number of donor or acceptor atoms are much higher than the NIOPI, then we can just assume that the charge carrier are just mainly coming from the holes or electrons created by that donor or acceptor. So just to wrap up in the kind of concept of the semiconductor on the direct and indirect band gap semiconductor. And again, because this is just related to materials, if let's say you want to know about the a little bit on the quantum kind of relationship between electrons and momentum, then you need to dig out a little bit on solid state physics, for example. But just to conclude here, in the direct band gap semiconductor, so an electron can actually be excited from the, sorry, this is supposed to be a valence band to conduction band without involving a change in the momentum of the electron. So when the excited electrons basically falls back into the valence band, so this electron and holes recombine to produce light, which is known as radiative recombination, and that's basically how the light emitting diodes, so for example gallium arsenide and a photonic in as LEG, is used when the electron that is actually excited to the conduction band kind of recombine back with the hole, and it will actually, because there's a change or there's a difference in energy, then the energy will actually be formed as kind of as a radiative recombination, and you can actually see light here. So the band gap of semiconductor EG can simply be tuned by tuning the materials here. So if you have a solid solution of aluminum gallium, the band gap will basically tuned, and the change in band gap will actually result in a change in the photon wavelength, and that's basically how we can see different light or different color. And just recap, the band gap is just related to Planck's constant multiplied by nu. Nu is just a frequency, Eg equal h nu, or just h times c divided by lambda, where c is just the speed of light and lambda is the wave. So h is Planck constant and nu is a frequency. In the opposite way, in the indirect band gap semiconductor, so the electron cannot be excited to the conduction band without a change in momentum. So when they actually comes back, so the electron and hole recombination will produce heat. And this is simply known as a non-radiative recombination. So an example here is silicon germanium. Just now for the direct bandgap semiconductor, the semiconductor is the kind of 3,5 semiconducting. So both direct and indirect can actually be doped to produce either N-type or P-type semiconductor. Right. So that's a little bit on the fundamental theory of semiconductors. And now I'm just going to spend probably about 20 minutes or 25 minutes or so to discuss about the applications of semiconducting material. And again, because this is the class is on materials chemistry or chemistry of materials, so I'm not going to talk a lot on the applications in the from the electronic point of view, but coming from the chemistry side. So I'm going to focus mainly on the photocatalysis here, which is actually the expertise of Prof. Setiabudi here. So kind of just a bit of introduction of photocatalysis. So it comes from a Greek word coming from light. So photo, post light, and catalysis or catalio, meaning that break apart or decompose. So basically what we want here is just a reaction. So mainly kind of a decomposition. So breaking apart some of the molecules here, or sometimes kind of the combination as well. That is actually initiated, or that is actually induced or helped or assisted by photon, and hence we need a photocatalyst here. So strictly from IUPAC, this photocatalysis, it is this is just simply a reaction performed in the presence of light photon here, and materials wise, this is a semiconducting material. So photocatalysis is just a photon-induced reaction that is accelerated in the presence of a catalyst. And the concept of catalyst here, just to reduce the activation energy without the catalyst itself being consumed in the reaction. So we have similar in the catalysis realm. So we have homogeneous and heterogeneous catalysis or photocatalysis here. So in the homogeneous photocatalysis, so the reactant and the photocatalyst, they exist in the same phase, come from this homogeneous here. For example, an organic dye here in aqueous form is actually degraded using photon, using carbon dots, but then these carbon dots are actually soluble in water. And in the other side of the photocatalysis, we have heterogeneous photocatalysis. So this one, as you can imagine now here, they actually exist in different phases, hetero. And for example, here, if you want to degrade some sort of organic molecules, or for example, in the process of water treatment, so we use a nanoparticle in the form of solid, and typically the famous one is titanium dioxide photocatalyst. So photocatalytic reaction are initiated by the absorption of a photon with the energy that is equal or higher than the bandgap energy of photocatalyst. And that's the reason why it's important to understand the concept of semiconductors and a little bit of band structure of semiconducting solid. And now you know very clearly that the absorbed photon will basically yield charge separation, because the electrons from the valence band will actually get excited or promoted to the conduction band, and will leave behind a formation of hole in the valence band. So now you got a charge separation. So the electrons now in the conduction band, and we've got the holes in the valence band. So now we are going to make use of that charge separation in our chemical reactions. So the excited electron here now will reduce any substrate or react with the electron acceptor. So for example, the oxygen dissolved in water, so that can actually get reduced to superoxide radical anion, so O2 minus in the radical form. Whereas on the other hand, the hole in the valence band here will actually react with, for example, with, for example, water or OH minus, yeah, hydroxyl ion, and they can actually oxidize into OH radicals. Or you can actually oxidize the organic molecules to form R plus. So now you need to know a little bit about the redox. So reduction and oxidation. So the excited electron will actually reduce, do a reduction reaction, whereas the hole will do the oxidation reaction. So the factors that will determine the photocatalysis, as you can already imagine, so we need the materials that has suitable electronic structure. Then we need to control the light or the photon coming in. Not only the kind of the photon coming in, but also the absorption properties of that photocatalyst. So because it's no point if you've got very good catalyst material, but the absorption is poor. And we need to understand the charge transport characteristics, as well as how long or how short the kind of the electron will actually stay in the conduction band. So the excited state life. So the examples of semiconductor photocatalysts, typically kind of oxide or sulfide based. So in the case we've got, for example, in binary, we have titania, zinc oxide, iron oxide. So the commonly 2,6 photocatalyst, cadmium sulfide, cadmium selenide here, zinc sulfide. We also have ternary. So for example, strontium zirconates, kind of all the perovskite material or lead chromate, or the chalcogenide kind of material, copper indium sulfide, copper indium selenide, or copper indium telluride as well. So in the quaternary, so we have bismuth aluminium vanadate, as well as casterite CZTS. So the common material here, copper zinc tin sulfide, or copper zinc tin selenide. So this is a good material for photocatalysts. So as I mentioned before, so the application can be in the degradation of organic molecule, in the water treatment, for example, in titanium and zinc oxide photocatalyst. And we can also use this to remove the kind of the trace metal. So for example, lead or mercury kind of pollution. So the mercury that is actually dissolved as a cation or ion can actually get reduced, and then we produce metal. Then we can actually separate that. So usually using titanium, zirconia, and we also have spinel, for example, nickel iron oxide photocatalyst. And the most popular one here is also a water splitting. So for example, in dye-sensitized kind of solar cell, or also in the photoelectrochemical water splitting. So it's not only coming from photon, we also need to supply a little bit of coming from the electrons, electricity. So the idea for this water splitting is just green hydrogen production. So you need you can actually produce green hydrogen from water. And obviously the other half cell reaction is you need to take into consideration the oxygen. And also the photocatalysis is used because it has antibacterial properties. So the bacteria can be decomposed when it's actually doing there is a photoreaction there, the photochemical sterilization. So the general principle here, so if you got the photocatalyst material here, we got the valence band, we got the conduction band here on the top here, and separated by the energy gap. We shine with the light with the energy of h nu, Planck's constant multiplied by frequency, or just hc divided by lambda. And we got charge separation. Electron goes to the conduction band, leave behind the valence band, leave behind the hole in the valence band. So what happened here when the electron is actually reacting with typically with the molecules that we want to degrade or we want to react, they has to be adsorbed. So there is an interfacial reaction here. So there's going to be a reduction kind of reaction here. You start with A, adsorb on the molecule here, reduction plus E minus will create A minus. Yeah. And whereas in the whole, there will be an oxidation reaction. So if you've got D, for example, then we've got reacting with H plus, then it will create D plus. So this is just kind of more kind of specific or more thorough explanation coming from various papers, and they start to make a general consensus on what happened during the photocatalysis processes. So basically, there are a few processes that can get involved. So it's not only just simply photoexcitation, then oxidation reduction. So yes, the first process you need to actually excite. You need to separate the charge. So we've got the reaction 1 here. So the conduction band electrons Cb with the charge carrier of -1, and valence band holes H plus Vb here are generated by the absorption of light by a photocatalyst. Yeah. So then, if we just take into consideration the electron here in the conduction band here, so the first one is similar to what kind of a generic mechanism of photocatalysis in the reduction process. So the conduction band electrons here will reduce the adsorb molecules. So from A from the solution, for example, then moving into adsorb molecule, then AAD, then reacting with the electrons, then we'll actually produce A minus AD. So that's the first reduction process. Or there is a possibility that this conduction band electrons does not actually interact with the adsorb molecule, but it can actually be kind of trapped on the surface of the photocatalyst. For example, because in the surface there's a lot of defect, or can be actually trapped in the defect. And so it's actually forming E with the subscript Tr minus, with the energy level kind of slightly lower there. And these trapped electrons can now reduce the adsorb molecules. So similarly, in the oxidation process, kind of initiated by this hole in the valence band. So the valence band holes, reaction number 5 here, can actually oxidize directly the adsorb molecule, in this case DAD, create then oxidizing, then you increase in the oxidation number here, becomes D plus AD. And similar to the electrons kind of going into the trap state, the hole in the valence state here can also be kind of trapped, move into slightly higher energy state on the surface of the photocatalyst, or on the defects, for example. And it will create, rather than H plus Vb, so we have H plus Tr, so Tr stands for trap. Then this H plus Tr will actually react with the D adsorb to create the D plus adsorb. So that's 1, 2, 3, 4, 5, 6, 7. And the last one that we have to take into consideration also the lifetime of this charged species regarding this recombination process. So the first one is the easiest one is that we can understand the excited electron in the conduction band moves back to the valence band. Recombination here, then we will actually generate light or generate heat, for example. So it's reaction number 8. Or these conduction band electrons can also be recombined, not with the valence band hole, but also with the trapped hole here. And similarly, the trapped electrons here will actually be able to recombine with either the kind of valence band holes, or the trapped electrons here can also be recombined with the trapped holes. So for each of these mechanisms, there is a rate constant. So I'm not going to discuss here in this lecture, but what you need what you can calculate is just simply a ordinary differential equation when you want to actually calculate the total number of, for example, electrons or hole per unit time, considering all those processes with respect to the AAD, the supply of reactants, as well as the product of the reduced AAD minus here, and similarly for the holes with the the DAD or D plus AD. So we can actually make a kind of a chemical reaction equation considering with all these processes, and from there we can basically calculate the rate of reaction, for example, and from there we can simply understand which one is the kind of the rate limiting step. So I'm just going to conclude with specific examples here, decomposition of organic compounds. So we understand just now. So this, we've got the valence band here, and we just concern here with the oxidation. So oxidation of a molecule by a auto-generated valence band holes here, H plus VB. So there are kind of various mechanisms here. So the valence band holes H plus VB here can actually extract the molecule, extract the electron straight away from the adsorbed kind of molecules and oxidize them. Yeah? So the molecules will get oxidized, got positive charge. Or the H plus VB here can actually be stabilized on the photocatalyst surface. So just now we understand about this trap holes, this H plus Dr. So that can actually oxidize the molecule. So it's the same as just now reaction number whatever here 5 and 7. So again, depending on the valence band holes or the trap holes there, which carries charge of +1. So the third kind of possible option here is the valence band positive hole can actually oxidize the surface hydroxyl groups or adsorb water. So this is oxidation, and this will actually end up creating the radical of OH. So OH adsorb minus, so hydroxyl here is just OH minus. So what you're creating here is actually OH adsorb, kind of OH radicals. And this OH radical is very reactive, and they can actually oxidize the molecules at the surface. So just basically number 3 here. And the last one, the possible explanation here is number 4 here, the generated kind of OH radical, or this dot OH. It can actually be released from the surface to the solution in this case. So we are talking about organic solution in the aqueous form, or in the, for example, in air, in vacuum, into the solution there. And this OH radical can basically oxidize the compound quite a distance from the surface of this photocatalyst. So the difference between these 3 and 4, the 3 here, the adsorb OH kind of radical here directly reacting with the molecule, oxidizing the molecule, where this one you basically release the radical, and that they can actually travel quite a bit of distance, and it can actually oxidize the molecule. So specifically for specifically for titanium dioxide here, for the decomposition of organic compounds. So there are various mechanisms, and this is one of the accepted one. So you got the photocatalytic oxidation in organic compounds, commonly accelerated in the presence of oxygen. So basically, when the light creates a charge separation, so the electrons will actually reduce this oxygen into kind of O2 minus radical, yeah. And when it actually reacts with H plus, so you can actually make it either hydrogen peroxide, or you can just simply make the HO2 kind of radical there, kind of yeah, with the kind of lone pair electrons. So let's kind of keep this first here. Then what happened in the whole state there? So the valence band hole plus here, as we discussed before, it can actually oxidize either the adsorbed water H2O or the surface hydroxyl, and it will create OH radical, so OH adsorb here. Then this can actually oxidize the molecules at the surface. So this kind of this OH plus or this H plus can actually react with this reactant here. So this RH, so for example, if you assume this is just a reactant with, for example, whatever here, R, alkyl group, for example, with hydrogen, and we'll actually create the R kind of radical here, R dot here by losing the H plus, and this R dot here will actually react with the radical coming from the reduced kind of chemical from the electron here. So for example, R plus R dot here reacting with the this O2 minus or HO2 minus, it will create the ROO minus in the presence of oxygen. And now after you got the RO minus, or what normally the photocatalysis or decomposition process takes place. So the R here will actually lose one of the carbon, and typically producing carbon dioxide, so CO2, and as a result, it will actually produce R prime H here. So it is alkyl group, you're kind of losing one carbon. So the intermediate from this typical reaction, is not only a simple reaction as R prime H here. It will involve, for example, aldehyde, so R prime CHO, but also can be in the form of carboxylate R prime COO minus. So if you can imagine here, the way that we try to understand the mechanism here is not very straightforward, because depending on the reaction, so we need to be able to actually characterize or analyze or even identify for each process. So whether you're actually forming a specific, aldehyde group or carboxylate group, because they have a specific fingerprint for us to know that. So sometimes just the issue of the time domain and the sensitivity of this particular intermediate before the final product is produced. So it's very, very complicated when we want to understand the rate limiting step or reaction kind of rate constant, for example, when there are a lot of steps involved, especially when there are electronic charge involved in the reaction. It's not only kind of a chemical reaction. So that's all that I want to talk today. So far we have covered this band theory of solids, then very clearly now concept of valence conduction band gap, intrinsic extrinsic semiconductor, a little bit on direct and indirect band gap. If you want to know more, then you need to read a lot on the kind of solid state physics, and a little bit on the on the photocatalysis application. So that's all, Prof. Setiabudi and students.
Okay.
Is there any questions? Just bang on 11:30.
Halo.
Oke, thank you Dr. Stevin. Oke, Bu Citra, please handle selanjutnya.
Ya, apakah terdengar suara saya, Prof?
Ya, jelas, silakan.
Ya, oke. Mohon maaf sebelumnya untuk Bapak Stevin Pramana atas kesalahan teknis di awal. Sebelumnya, saya ingin memperkenalkan kepada para peserta di sini tentang latar belakang dari Bapak Stevin Pramana ya. Jadi Bapak Stevin Pramana di sini adalah seorang lecturer di Newcastle University. Mari kita tunggu sebentar untuk PowerPoint-nya. Kemudian beliau mengajar di School of Engineering Newcastle University dan memiliki keahlian di bidang kristalografi, elektron mikroskopi, fuel cells, dan juga electrochemistry. Kemudian untuk latar belakang pendidikannya, Bapak Stevin Pramana ini mendapatkan gelar PhD di Material Science and Engineering dari NTU dan juga Bachelor of Engineering, Material Science and Engineering. Kemudian untuk working experience saat ini menjadi lecturer di Newcastle University dari tahun 2017 hingga sekarang. Kemudian melakukan postdoctoral research associate di Imperial College London di tahun 2013 hingga 2017. Selanjutnya menjadi research fellow di Nanyang Technological University Singapura dari 2011 hingga 2013. 2013. Kemudian untuk research metriknya, Bapak Stevin Pramana telah menghasilkan sebanyak 85 paper dengan di dalam jurnal-jurnal yang bereputasi tinggi dengan citasi sebanyak 4.600 dan H-indeksnya adalah 37. Kemudian ini merupakan beberapa publikasi terbaru dari Bapak Stevin Pramana. Mungkin teman-teman ada yang memiliki ketertarikan di bidang fotokatalisis ataupun di bidang semikonduktor, bisa untuk menjadikan referensi ya untuk selanjutnya. Kemudian jangan lupa teman-teman untuk mengisi form kehadiran, silahkan untuk di scan barcode ataupun mengisi Google Form yang sudah saya sertakan di komen. Nah, sekarang adalah saatnya untuk sesi tanya jawab. Dipersilakan kepada teman-teman untuk memberikan pertanyaan kepada Bapak Stevin Pramana, mohon maaf, bisa secara ketik atau bisa secara langsung. Silakan. Baik, ada pertanyaan teman-teman? Baik, ada satu pertanyaan di sini dari Bapak Fatir Azet ya. Thank you, Dr. Pramana, for the well explanation. I would like to ask, how do we determine the P and type behavior of metal oxides or sulfides semiconductor theoretically? Kepada Bapak Stevin, silakan untuk memberikan jawaban.
Baik, terima kasih Fatir. So, so typically when we want to actually understand this metal oxide or sulfide semiconductor, so the P and N type kind of behavior is typically controlled by the defect. So, for example, if you've got, for example, a vacancy on the cation side or vacancy on the anion side, that will actually lead to the different type of P or N type behavior. So if you want to determine that, so it's kind of the easier way is if you just put like a whole effect there, then you'll actually basically know whether you actually get positive or negative bias. And I think if you try to actually use I think if you've got kind of electrochemical method, then you can actually try to determine based on when you actually sweep towards the positive or negative side, the P type or the N type behavior. But typically, if you just apply kind of different potential behavior, then you'll know whether it's actually P or N type. So in a typical case, for example, catalyst for let's look at, for example, for the oxygen reduction reaction in let's say alkaline condition. So for water splitting or electrolysis, let's say if you've got let's say perovskite, lanthanum cobaltate, then typically they involve in P-type semiconductor. The way sometimes we can actually tell that also is if you have a facility to control the oxygen partial pressure, for example, because the conductivity is going to be different at different oxygen partial pressure, because the oxygen vacancy on that particular perovskite this is determined by the PO2.
Baik, kepada Bapak Fatir Azet, apakah sudah cukup untuk jawaban dari pertanyaan Bapak atau ada yang ingin ditanyakan kembali? Silakan Pak. Baik, mungkin kepada peserta yang lain jika ada yang ingin ditanyakan, mungkin jika ada mahasiswa di sini yang penelitiannya terkait dengan fotokatalis, kemudian semikonduktor, mungkin juga bisa menanyakan tentang mungkin
Ayo silakan. Bahasa Indonesia boleh, Dr. Kevin can
Ya,
understand bahasa
boleh bahasa
very well.
Indonesia.
So no worry with bahasa. Ayo, Virgi, Sila, ayo, Mas Roni. Ada? Ada silakan. Ini siapa nih? Ada yang mau tanya? Jangan
So
malu-malu.
So whilst you are preparing for questions, another opportunity also, because in the UK we have good central facilities, so Prof. Setiabudi knows very well. Kalau teman-teman punya ada konsep atau apa namanya research proposal buat misalnya tes di synchrotron, misalnya mau tahu apa namanya XPS, but for example at ambient temperature, or beberapa teman-teman yang spektroskopi in for example femtosecond atau apa gitu. Di UK asal proposalnya itu diterima itu nggak ada biaya gitu ya. Jadi we just need to apply for beam time. So in the UK we have synchrotron X-ray, we have neutron, and some of the research group are interested to understand the movement of ions, so for example lithium. So you can actually trace that lithium movement using muon. So the muon will actually, tag along with that particular lithium, for example, and you can understand how the lithium actually moves. So very good opportunity, and I think in some cases I know for sure there are various options for Indonesian and Malaysian. They focus on providing opportunities for Indonesian and Malaysian researchers. So basically, they've already secured some beam time. But as far as I know, the receptance or the acceptance from Indonesian kind of friends or colleagues are still very low. So
Okay.
most of the beam time are not fully allocated.
So, Dr. Stevin,
Yeah.
does it mean that we can, for example, in some cases, we got difficulties with XRD analysis because in Indonesia, most of XRD is dedicated for powder analysis, right? Kind of bulk sample. But for our cases, our sample is kind of very thin film. Like in the last cases, the two of my students synthesize gold
Yeah.
over CiO2 within very thin gold, and it is difficult to get diffraction pattern of gold, right?
Yeah.
But when I send the sample to Malaysia, to UKM, for example, you got a very good result. So
Yeah.
is it possible if we sometimes, maybe next time, send the sample to your lab for some analysis?
Yeah, it is possible. Usually for XRD, if let's say we want to go or analyze the thin film of XRD, so we can't really use the bulk configuration because the bulk is using Bragg-Brentano, so meaning that
Yes.
the theta is coupled. So
Yeah.
what normally people will do is using grazing incident extra diffraction.
Yes.
So usually we set the incident angle probably 1 or 2 degrees, because with 1 to 2 degrees the interaction volume is already probably like 100 nanometers or so. Then what the diffractometer will do is just scan the theta from the detector side. But the issue here is, I mean, in most of machine, theoretically you can do that. But the issue with low angle or grazing incident extra diffraction here is the beam from the primary side, so the beam from the source to the material or the sample, it must be fully collimated. So usually people use parallel beam. And
Okay.
the normal breakband tunnel, they use kind of divergence because they want from the, for example, from the line focus or from the point focus, it has to go all the way to the sample because of the statistics. Then after that, coming back from the convergence, coming back to a focus. But then in the grazing incidence, you need parallel beam. So typically people use, in XRD, we call it global mirror. So there's a mirror there, then just put that parallel. Then after that, coupled with good detector, what do you call it? Detector attenuator, because what you don't really want to end up here, because it's 1 or 2 degrees, you will actually hit the detector straight away. So there must be usually in the modern diffractometer, for example, from Bruker, they have automated attenuator. So they have like different slits of copper with different thickness, kind of in and out, and they can actually attenuate the X-ray intensity coming to the detector. Because otherwise the detector will get blind and most often it will get burned
I see.
and fail. But yeah.
Okay, but
So
as I know, in grazing incident, we can go as small as 0.5 degrees, right?
that's correct. Yes. So if you've got very good films, if you go like 0.5 degrees, then you start to see not only diffraction at high to theta, but probably the first 1 or 2 degrees. Then you will see the apa namanya Pak, like interference. Then you
Yes.
can actually check the thickness of the sample because you've got the different density, and that will relate to different scattering. Yeah.
Yes. Okay, because in case of our samples, the copper oxide crystal is very huge, right? Very large.
Yes.
So
Yes.
it's make us very difficult to get a good diffraction of very thin layer uh, of the gold.
Yeah.
So that's the problem. Uh, so I'm thinking to go to very small angle with grazing incident, and we have tried to do that in Malaysia, and we got a good result.
Yeah. And Prof, when you want to analyze the gold, so you just want to know whether gold exists, or you want to know whether gold is actually making intermetallic. Because if you just want to make sure that gold exists, then probably you don't really need
Yeah,
XRD. Yes.
yeah. For just for to get evidence that the gold exists, we can do it using XPS, and also and we did it by using XPS and also EDX, right? But we
Yes.
also want to know the structure of the pairs of the gold that's
Right. Okay.
that ground over the copper oxides.
Yeah. 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 Yeah.
We actually have tried to examine our samples using
Mm.
STEM,
Yes.
scanning transmission electron microscopy. I sent the sample to JAIS in Japan, and we got a good result actually.
Yeah.
And we can see very clear the thin layer of gold, but
Yes.
the problem, we still want to know the structured information of the gold. Uh, for example,
The
like
FF
the
the FF
crystal size. Pardon?
the FFT-nya nggak kelihatan, Prof.
DFFT.
Di if you do Fourier transform on your
Mhm.
kalau apa dari STM resultnya
Okay.
itu high enough magnification, hopefully you can
Mhm.
see a little bit of you know uh, the arrangement of atom. Terus kalau
Mhm.
dipakai fast Fourier transform, normally you will get the diffraction pattern.
Nah, itu enggak. Ya,
Tinggal di FFT aja, Prof. Kalau misalnya
DFFT ya.
kelihatan ada, ya pakai
Oke, saya coba
FFT,
ya.
ya di download image J aja kalau nggak, Prof, pakai image J, terus di
Hmm.
areanya yang mau diiniin, terus apa ada dia langsung ada FFT-nya, terus dia langsung dibikin diffraction pattern-nya. Tapi
Oh, oke.
provided apa namanya sampelnya itu ada karakteristiknya gitu ya. Jadi high
Hmm.
enough magnification lah, mungkin sekitar minimum like 100 200,000 150,000, then you
Hmm.
start to see. Ya 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 ya.
Ya, ya, ya. Oke, oke. Saya rasa itu harus dipelajari ya. Saya belum pernah coba itu.
Ya.
Menarik, Pak. Oh, dari STM bisa dapat. Oh iya, lattice
Yeah.
springs kan ya, saya. Tapi kalau kalau dari cross section itu sulit kan?
Ya kalau resolusinya bagus, kalau apa preparationnya thin enough, harusnya tetap bisa lihat sih. Atau ya
Hmm.
kalau kalau enggak ya berarti si goldnya itu amorphous gitu ya, nggak cukup waktu untuk crystallize,
Ya, ya, ya.
which is very unlikely sih kalau nggak tahu goldnya itu di solution base atau pakai physical deposition
Uh,
atau apa.
using electrochemical deposition.
Oh ya harusnya harusnya
Ya,
crystalline sih ya.
ya
Ya,
makanya itu sebetulnya.
ya.
Tapi kemarin itu kita sebetulnya STM itu kita buat mapping. You do mapping, elemental mapping.
Ya.
Jadi we don't take any kind of lattice springs, right?
Iya, kalau
Ya,
elemental mapping ya biasanya low magnification ya.
ya
Heeh.
kita buat kemarin di sensei yang di Jepang buatnya itu.
Ya, ya, ya,
Hmm.
ya.
Karena mungkin saya mintanya untuk lihat gold saja, tidak ini.
Harusnya
Tidak.
kalau misalnya mau itu nggak usah pakai stem, juga pakai TM biasa juga bisa sih, bro.
Tapi kan
Langsung.
kita harus buat sangat tipis kan? Itu problemnya kan, STM.
Oh, TM ya tipis, stem juga harus agak tipis sih. Cuma masalahnya kan kalau chemical distribution itu nggak bisa pakai tem kan, harus stem.
Hmm.
Harus
Iya,
stemnya itu kan,
iya,
ya
step.
stemnya stem EDX atau stem hadaf misalnya ya.
Iya, ya
Jadi
betul.
energy filter TM gitu ya.
Hmm.
Ya,
Oke, oke. Oke, thank you, Dr. Stevin. Silakan.
ya semua, bro.
Ya,
Ada yang mau tanya?
ada lagi Pak yang mau bertanya ini
Sila nih, Sila.
dari Sheila Norin Zahra. Thank you for the lecture, Doctor. I'm Sheila. From your explanation, it seems dopant affect the energy of the material host. Is it possible metal loaded they don't interfere the crystal structure of the host on the main material to affect the gap energy of semiconductor? Silakan.
Uh, I don't think it is possible, because once you dope the metals, then the structure is going to be changed. So the structure is going to change both physically, meaning that you'll see some strain. So the from the you know the bond distance, and the unit cell is going to be different. It's going to be expanded or contracted depending on the dopant, and as a result, then obviously the band structure is going to be different. What is actually interesting in the in the dopant, so in a lot of cases, if let's say you can try to vary or modify in such a way that the dopants will actually be in such ordered position, that will actually make your properties going to be interesting. So for example, when just now I did mention CZTS, yeah, so for example, copper 2, zinc, tin, selenite 2. So what we understand here, the tin and the zinc, they're actually in the crystallography, in the chemical term, we call it disordered. So we don't really know which part of the structure contains tin, which part of structure contains zinc. But then if you can do in such a way that you have CZS, so copper zinc sulfide 2 or selenite 2, then on top you have copper tin selenite 2, then your structure is going to be completely different. And the issue here is for those of you who are doing computational chemistry. So that's always the case from that will be asked by them, because from us as the experimental chemists, or sometimes as experimental material scientists or material physicists, so usually we can just assume that the occupancy of a certain host plus the dopant is X. Yeah. So we can't really differentiate whether a particular unit cell is occupied by host or is occupied by dopant. And we can just do a kind of an average structure. But then when we are talking about DFT, for example, then you have to actually know where your dopant is actually positioned. Because when you move your dopant to a different lattice site, or to a different interstitial site, your band structure and your energy is going to be different. And that's actually the kind of the challenge coming from theoretical kind of physicists or theoretical chemists, because they have, especially with low concentration of dopant. Yeah, just now we looked at, for example, in the p-type or n-type, we are talking less than 100 per 1 million of silicon. So how are you going to put that particular dopant when you are trying to do a simulation? So you need to have, a good permutation or combination to actually capture the whole contribution, the whole energy. And to make kind of situation more complicated or worse, that's whatever that the DFT is calculating is mainly on kind of at 0 Kelvin, and at the application where we are doing, the temperature is not 0 Kelvin, so the atom or the ion or the donor or the acceptor can actually be very, very mobile. So you just need to be very careful when you try to combine the theoretical kind of calculation from whatever DFT. Usually you can actually combine with MD, for example, if you know the potential, force field, for example, then just try to be cautious. Just try to understand this with a pinch of salt. So the theoretical can actually guide, but sometimes is oversimplified.
Terima kasih atas jawabannya. Kepada Sila, apakah jawaban sudah cukup atau ada yang ingin ditanyakan kembali? Silakan. Baik, sepertinya tadi saya melihat di April angkat tangan ya. Mungkin ada yang ingin ditanyakan secara langsung. Silakan Mbak di April.
Iya Ibu, terima kasih Bu Citra. Thank you for the insightful presentation, Dr. Stevin. I'd like to ask maybe personal experience during your experience synthesizing semiconductor materials. Have you ever had repeated synthesis failures, even when using the same material and parameters? Because I often get the inconsistency physical results in synthesizing the thin film material, even the parameters are the same. Maybe what I want to ask is, menurut Bapak, faktor apa saja yang bisa mempengaruhi ketidakstabilan dari hasil sintesis tersebut, Pak?
Okay. If I can actually give 1 or 2 tips, NINDI itu partikelnya nanopartikel buat di deposit di thin film ya.
Iya Pak, CO2O.
CO2O. Terus surfactantnya, itunya apa? Apa namanya? Reaktannya apa? Copper nitrate, copper
Prekursor.
Copper sulfate.
Copper sulfate. Terus di reduce atau
Gimana Pak?
soalnya biasanya kalau saya kan lebih ke nanopartikel tapi di solid gitu ya. Jadi saya lebih simple ketimbang kamu nanti yang harus deposit di substrate. Even with just producing nanoparticles for catalyst, in most cases, so usually I use nitrate base. And then after that I use ligand. So typically I use salt gel. So if you have heard Pacini method, so basically, usually I use, for example, ethylene glycol. Then sometimes I add PVP or PVDF. Just basically like a surfactant, and as a binding agent when the molecules is in the aqueous state. So yeah, then once the gel is basically formed, then I combust it at, for example, I don't know, 150, 120 degrees. So I put a little bit of fuel there. So sometimes people use hydrogen or glycerol or this thing. Then after they've got the nanoparticles on the low temperature state, then when I want to make it a little bit more crystalline, then I sinter it. Jadi biasanya itu yang bermasalah itu kalau di sintesis yang saya biasa ininya, yaitu apa namanya proporsi dari si surfactant atau proporsi dari ethylene glycolnya with respect to metal cations, sama seberapa cepat combustionnya itu berlangsung itu. Jadi even stirringnya to make a gelation process, gelation for 6 hours, gelation for 24 hours, the quality later on is going to be completely different. NINDI masalahnya itu you got phase separation, atau you've got completely apa namanya filmnya pecah atau apa?
Like the physical result, the deposit copper oxide sometimes merah bata, terus kadang ada hitam-hitamnya gitu, terus ada kuningnya juga kadang.
Itu
So I don't know.
oxidation dong. Berarti
Um,
copper oxidation state-nya nggak sama. Berarti ada yang +1, +2, atau mungkin ada yang sampai 0 kali kalau sampai orange.
Maybe sih, Mister, karena parameter yang digunakan itu sama semua kayak konsentrasi larutan, terus potensial applied-nya juga sama, pH-nya juga sama. Jadi mungkin iya benar di oksidasinya mungkin.
Iya, kalau mau itu ya, kalau misalnya mau fully oxidized gitu ya nggak tahu di reaksinya itu dikasih more dissolved oxygen atau saya nggak tahu sih, harus harus di control environment-nya ya.
Iya mungkin. Oh,
Oke, kontrol
Iya.
kontrol ini kontrol sintesisnya.
Iya, dia control environment. Temperature-nya dikontrol nggak, Ninji? Pakai
dikontrol.
pakai apa?
Pakai water bed.
Pakai water bath. Oke.
Mm-mm.
Eh, iya sih
There's
paling.
certain manufacturer that uh, could influence their synthesis process actually because they use electrochemical method to grow the copper oxide. So kind of
Mhm.
impurities and other control parameter may affect the result actually.
Iya. Kalau di electrochemistry, Prof. Jabudi harusnya lebih lebih expert di sini. Kadang electric field-nya is gonna be very very important. Substrate-nya, kalau substrate-nya ada apa namanya dirt gitu ya, itu jadi antar dua potensi, dua reference potensialnya itu bakalan beda gitu, electric field-nya. Dan that it will affect the how the nanoparticles will be deposited.
Okay,
Terus
Dr. Stevin,
solution,
my last question.
yes.
When we grow a very thin layer, metallic layer on semiconductor, do you
Yeah.
think that it can affect the band gap energy of the semiconductor?
Uh,
Because in I thought that since the metallic layer do not change the structure of the semiconductor, so it should not change the the band gap, right?
yes. Um, if I think the issue here is the band gap of semiconductor far away from the metal, it won't actually get affected. But then at the interface there will be apa namanya Fermi levelnya itu harus align. Jadi biasanya
Yeah,
itu
yeah.
bakalan ada band bending atau ya band bending either p-type atau n-type gitu ya. It's the same as the concept of in electrochemistry, Prof. Yang kalau electrode terus ada semiconductor terus ada solution. Jadi, itu kan
I
dia
see.
ada
Interface,
apa
yeah,
namanya
interface.
base-nya ya ada ada electric double layer kan.
Mm,
Jadi ada Helmholtz, ada apa satu lagi itu loh. Nah, itu
mm,
kan itu bakalan efek karena potensialnya itu at the interface itu harus sama gitu kan.
yeah, yeah.
Sedangkan jauh itu keluar gitu. Iya, iya. Jadi itu bakal ada band bending band itunya sih, Bro.
Berarti itu sebetulnya possible ya untuk merubah kemudian hasil hasil apa namanya eh, hasil ujinya ya, meskipun struktur itu tidak berubah ya, karena
Iya, makanya
ada interface itu ya.
betul, makin kecil dia makin 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 apa namanya makin makin pronounce ya.
Hmm,
Terus nanti kadang di apa namanya di interface-nya itu juga bakalan nggak distinct gitu, Prof. Jadi bukannya A
hmm,
langsung ketemu B, di sini kadang ada interlayer gitu. Either
ya.
for example, iya kan kalau dari sisi fotokatalisis kan nanoparticle different
Hmm,
different size bakalan ngefek gitu ya, ada
ya,
quantum effect-nya gitu. Iya.
ya, karena
Yang
dia
pasti kalau Aha.
karena berarti dia ketika absorbansi foton kan itu terpengaruh juga kan ya.
Ya,
Karena
iya.
nanopartikel kan akan menyerap foton juga ya, berarti kan akan berbeda ya. Oke, oke.
Iya, iya.
Ya.
Itu sama kayak converters ya, Prof. Surface enhanced Raman kan
Hmm,
biasanya di atasnya dikasih lapisan tipis gold gitu ya.
ya, ya. Iya
Terus
betul
ya
betul.
scatteringnya bakalan lebih gitu. Iya, iya karena ya.
Oke, oke. Oke, Bu Citra, terima kasih banyak nih, Dr. Stevin. Saya
Thank you,
rasa
Bro.
ini udah pukul 6 lewat, Dr. Stevin udah waktunya break nih.
Iya,
Sebelumnya ini Prof memberikan secara simbolis sertifikat kepada Bapak Stevin ya Prof.
baik. Thank you, Citra.
Ya, ya boleh silahkan ditampilkan nih oleh-oleh buat.
Ya, jadi silakan pada
Ya, Dr. Stevin, ini kenang-kenangan dari
Baik,
walaupun belum muncul nih dari prodi kami ya.
iya.
Terima kasih sudah berkenan, waktunya, ilmunya sangat luar biasa ya, memberi pencerahan ya. Mudah-mudahan tidak kapok nanti kalau diundang lagi ya, Dr. Stevin.
Baik, Prof. Iya.
Oh,
Ini juga agak mendadak juga kan ini.
iya,
Jadi
iya betul
saya saya
betul.
nggak saya nggak tahu apakah materinya itu pas atau apa gitu. Jadi lain kali kalau bisa di refine gitu kan. Jadi lebih lebih apa? Lebih lebih bisa diterima sama teman-teman mahasiswa gitu ya.
Ya, ya. Ini maklum karena ininya kan mahasiswa S1 semua ya, Dr.
Iya,
Stevin. Jadi mereka juga baru baru belajar seperti itu. Tapi saya rasa cukup menarik ya. Terima kasih banyak. So a big thanks to you, Dr. Stevin, for an excellent lecture. We truly
makasih ya.
appreciate
Oke.
your times and apa namanya the knowledge that you have shared to us. Oke, terima kasih sekali
Makasih ya.
lagi.
Ya,
Sampai ketemu ya. Semoga sehat selalu, sukses. Semoga nanti Agustus bisa menyempatkan ketemu ya kita
ngobrol-ngobrol. Ya, baik.
ngobrol-ngobrol.
Thank you.
Terima kasih.
Thank you, Prof. Ayo, mari semuanya.
Sama-sama. Thank you so much.
si peserta jangan lupa untuk mengisi daftar hadir ya. Baik, karena sudah jam 6:04 ya, jadi sesi ini saya tutup. Terima kasih atas kehadirannya kepada Prof. Stevin dan juga Dr. Stevin Pramana dan juga para peserta yang hadir. Silakan untuk bisa meninggalkan room Zoom. Terima kasih.
Udah ya Bu Citra ya, pamit ya.
Ya Pak, silakan Pak.
Ya, Assalamualaikum.